Arctic and some of the concepts that you guys have talked about in the curriculum. And I view this as an opportunity to give you guys some additional resources to think about this and learn about it with real data that are happening every year, and you could modify and put in your curriculum and have your students look at. And then also just to be a resource for you all, because I know you may have questions, and just help you kind of build that expertise and that confidence so that you feel like you can really effectively understand and interact with your students. And so I want to say, if you have questions or we don't get to things today, you can find me just by Googling me to my CU webpage and stuff, and find my contact information, and feel free to shoot me an email. I'm happy to answer questions after today as well. So I will share my screen and put this on. Does it look good? Great. Okay, so understanding Arctic warming using observations and models. This is basically what I do for a living. And I'm really excited to share some of the resources and ideas that I think about in the context of these questions. This is a photo that I took in Churchill, Manitoba, which is on the shores of Hudson Bay. And the polar bear there is one of about 900 that congregate on the shores of Hudson Bay before it freezes. And then the polar bears go out on the sea ice that forms on the bay. And so this is just one example of a place where the Arctic is very accessible, and there's a lot of interactions between humans and bears and sea ice, but there's others as well. And it's also a location that's really changed a lot, and where there's been a lot of Arctic sea ice loss with a lot of associated impacts, not only on polar bears, but on people and other aspects of the environment as well. So for a different perspective, we were looking, can you see my cursor? If I move it here. This is Hudson Bay here.
Yes, we can.
Yeah, you can see, okay. This is Hudson Bay here. This is actually a satellite image. This is what you would see with your own eyes. This was, it's a mosaic put together from a bunch of different images from yesterday, so June 29th. And so here's Hudson Bay here. And we're looking down at the central Arctic. The North Pole is kind of under all of this sea ice up here. Greenland, 7 meters or 20 feet of sea level rise equivalent in the ice that's on the land there. But then the Arctic here at the North Pole here, this is the Arctic Ocean. And at this point, at this time of the year in June, it's covered with sea ice. I like this image also because it really conveys that there's a lot of other things going on. And in particular, you might find it fun to just pull up these kind of image of the days and kind of look with your students at what you might see in the Arctic on a given day. And that might help kind of motivate and think about what some of the processes are that are important for driving Arctic change. So one of the things that I see when I look at this image as well is a lot of clouds that are pretty bright and reflective, just like the ice that's bright and reflective. And you can talk about that in terms of the concepts of albedo and kind of what's going on in the Arctic in any given day. So here's another one of these images. This is actually from September 15th, 2020. This is last early fall. This was actually the day in 2020 when the Arctic had the least sea ice cover of the entire year. So usually we have a minimum in the amount of sea ice in the late summer, and in 2020 that happened on September 15th. You can see though, you can't always tell that that's what's going on here, right? Because some of that Arctic Ocean is obscured by cloud cover. So again, we can also look at these images, you start to see this little dark spot that appears right at the North Pole. And I think this is useful for thinking about like what it is, how are we actually able to see what's going on here? And the reason that we can see is because this is a satellite that's operating in the visible wavelengths. So it's the same wavelengths we see with our eyes. And of course, the Arctic gets really dark in the winter. And so as we start to transition into the dark months of the year in the Arctic, there's some places we can no longer see. So if you look at an image like this, for example, in January, you won't be able to see anything because there's no visible light in the Arctic in the middle of winter. So again, just kind of fun, I think, you know, really visual and kind of entertaining to see. So the question that you guys are addressing through this training and with your students, you know, why is the Arctic warming twice as fast as the rest of the world? I just want to say that this is a very active research question too. You know, we have some of the answers to why this is happening, but there's a lot of things we don't know too. And I think that's one of the reasons I really enjoy being a scientist, is trying to test different hypotheses and understand what's going on. And we have a real opportunity to understand what's going on because we're observing this change happen, you know, right before our eyes. And I think it's important to emphasize that both observations and models are really needed to understand the processes that are underlying climate change and variability. And that includes what happens in the Arctic. And we had some discussion when we did this workshop the last time about what a model is. And I'll get into that. I know you guys probably think about this in terms of conceptual models, which I think is a really nice way of thinking about just putting the different pieces together and how they relate to each other. But kind of another way that scientists use models is we run numerical models, and basically it's the same idea as a conceptual model. It's just that we're putting a bunch of equations that describe sort of the theory or the physics that underlie the processes that we're seeing and trying to solve those equations all simultaneously. And sometimes when we do that, we can get answers to questions that, you know, we quantitatively that we can't get when we just think about a conceptual model. So we say, you know, this factor is important, this factor is important, and this factor is important. A model helps us quantify their relative importance. So obviously all tools we can use, we will, but there's some caveats that come with the tools that we use. Observations are incomplete. You know, we have measurements that show where the Arctic sea ice is and how warm the Arctic is, you know, for longer than we have, for example, measurements of the outgoing long wave radiation or the absorbed shortwave radiation. So we have to just work with what we have. And also all models are wrong. You know, we're always going to exclude something from them. They're not going to be perfect. That's not really the point of a model. The model is meant to just bring together all of the things that you think are important and kind of put them all at the table to make sure that you can consider them all and understand how they interact and what their relative importance is. But they should always be taken with a grain of salt because you could be missing something. And if you're missing something big, you know, your model is definitely going to be wrong. So there's lots of ways to observe the Arctic. You guys have talked some about MOSAIC, this expedition to the Arctic where, you know, scientists were boots on the ground, making measurements, you know, flying unmanned, unpeopled aircraft. So there's a lot of things you can do in situ, but that ends up being very expensive and also sort of limited in the time and space that you have data from. Satellites can be really helpful for kind of filling in those kind of big picture gaps because it gives you, as we saw with those visible mosaics of the entire Arctic, kind of this bird's eye view of what's happening everywhere. And we have those, you know, for multiple decades for some measurements, which is really, really nice. We also can look further back in time. And one of the ways that we do that in the Arctic in particular is using ice cores. So we can drill down into the Greenland ice sheet. Every year there's a layer of snow that turns into a layer of ice. And we can actually probe what's happened into the past many thousands of years by looking at these layers in the ice cores. So the picture here is actually of the Ceres instrument. So this is the instrument that's measuring the outgoing long wave radiation and the outgoing short wave radiation. So both the long wave and the short wave from space. And it does so globally so that we can look and see kind of how the Earth's radiation budget is changing. Here's another example of some satellite data that you're using. This is the observed Arctic sea ice loss. So what we have here is for September, the amount of the Arctic Ocean. So it's measured in terms of an area, million kilometers squared, that's covered with sea ice. So the amount of the Arctic Ocean that's frozen, basically. And we can see that since these satellites started in the late 1970s through to the present, this last data point came from September 2020, that we've seen a pronounced decline in the amount of sea ice on the Arctic Ocean. And these measurements come from satellites that measure in the passive microwave, which is a much longer wavelength than what you see in the visible or what gets emitted as long wave radiation. But this passive microwave is really good for seeing through the clouds. And so it really helps you see where there's sea ice and where there's not. So in addition to the pronounced decline, we can see there's a lot of interannual variability. So for example, 2020 was the second lowest Arctic sea ice extent or Arctic sea ice cover on record in September that we've ever seen in this record. But the big minimum before that was in the summer of 2012. And there's also a pretty big minimum here you can see in 2007. So these extreme years tend to get a lot of attention, but I think it's also important to recognize that they're part of this kind of longer term climate trend here. And this is something that we cannot explain with natural variability alone. So it's really one of the big fingerprints of human caused climate change. So these numbers, trying to put them in perspective is of course really important for all of us. So this is just the area of the Arctic sea ice on September 20th, 2012. So that was the day of the minimum sea ice cover in that year, 2012. And then here in blue, we have the median minimum area. So you can see, these are huge deviations from what is kind of in the average of this time period here from 79 to 2000. And you can see this by looking at something like the entire US. The Arctic is a pretty big area, and the amount of Arctic sea ice cover, it's like the equivalent of moving the border from somewhere in Mexico to like the middle of the US. Like these are big changes in where the Arctic sea ice is. We focused some on September here. Again, that's the month when we have sort of the minimum amount of Arctic sea ice cover. And this is just showing the Arctic sea ice anomaly from September 2020. So you can get a visual sense here. Here, anomaly is used with a very specific meaning. It just means departure from the long-term average. And the average here that we're using is 1981 to 2010. And so what we can see is, compared to that long-term average, a 30-year average, there's a lot of the Arctic that was below that long-term average in September of 2020, which is consistent with that year being, the second lowest sea ice cover on record. I also pulled out just last month's data, which were just put up, really recently, May 2021. And we can see, definitely areas where, again, the blue colors here indicating that there's less sea ice cover than the long-term average. But you can see the regions where we're losing Arctic sea ice cover in any given year, they kind of change. And then they also change seasonally. So, in May, we're tending to lose sea ice more along the perimeter, which is out here maybe in the North Atlantic, getting towards Scandinavia. Whereas when we're in September at the minimum, we're losing ice, in the central Arctic and in that region. So there's some links here. You can always make your own maps. This would be a great resource to maybe pull up and kind of discuss with your students, where things are happening and why. So I'm going to finish here with a little bit of discussion about what I mean by a model. So I kind of alluded to this earlier. So I often use numerical models. These models, they consist of a lot of simultaneously solved equations that describe climate processes, and they're run globally. And they're run for a bunch of different model components. So we have an atmosphere model, a land model, a sea ice model, an ocean model. And we try to put them all together, put all those processes together and conserve energy and heat and water, and look and see what are the processes that are controlling the climate. And these models are really big, the ones that I use. So I'm often running them on supercomputers, including the one operated and owned by the National Science Foundation called Cheyenne, which is in Cheyenne, Wyoming. So unlike conceptual models, these numerical models are really helpful because they really let you test hypotheses and understand and quantify the relative importance of different processes, and of course, to make future projections. So if you have, a model of an entire system, and then you ask, how is this going to change into the future if we, for example, increase greenhouse gases, or if the sun gets dimmer, we can use this model to try to understand what the consequences of those different changes and kind of the drivers of the climate system might be. So here's the graph. Actually, we made this graph in response to some of the questions that we had from teachers last year in this workshop. We were looking at the spatial pattern of warming in response to increasing greenhouse gases, and in particular, the increases in greenhouse gases from human activities. And what we can see here on the top is just the change in surface temperature calculated by one of these Earth system models. And you can see the Arctic in particular is warming a lot more than the rest of the globe. So that's consistent with the observations as well. And there's this very distinct spatial pattern here, like the land warming more than the ocean. This like high latitude warming is definitely prominent. If we look at like what is driving that warming in this Earth system model, we can see the change in surface atmospheric carbon dioxide. So here what we're looking at is where the increases in greenhouse gases are coming from and what they look like when they first are at the surface here. So we can see major population centers in the northern hemisphere. We see larger CO2 concentrations at the surface in the northern hemisphere than in the southern hemisphere. And that's just associated with kind of where the industrial activities are that were generating carbon dioxide, the greenhouse gas in this case. It's really interesting. And I think one of the things that was kind of striking to the teachers is just how different these two maps look, right? Like the map on the top is kind of like the response. What do we see in response to increasing greenhouse gases? And the map on the bottom is, kind of how did we force this? What is the driver of this response? And so these spatial patterns do not have to look the same. And it just illustrates some of the complexity of the climate system in terms of, where the system is the most vulnerable to respond is not necessarily the same place where the greenhouse gases are increasing. So just finish here with an example of how we're trying to use models and observations together to try to understand the changing Arctic. And this is a paper that was recently published that I'm a co-author on. The lead scientist is Alice Duvivier, who got her PhD here at the University of Colorado and is now a scientist at the National Center for Atmospheric Research. And she was answering this very broad question, like what are the causes and consequences of the sea ice being younger and thinner? When we all want to be younger and thinner, but that's what the sea ice is getting right now. So here we have it, the old Arctic on the left and the new Arctic on the right. And basically what this study did was asked, if we were to do a year-long field campaign in the Arctic in a ship and just see where the ship might drift, how would the fact that the sea ice is younger and thinner, how would it change how our ship might drift in the Arctic Ocean? And one of the things that was super interesting about this study is that it found that with this younger and thinner sea ice, that the ship tends to move faster. So there's not as much resistance from the ice because it's thinner. And also the paths tended to be a lot more variable. Like, so the ship would sometimes drift into places that it wouldn't have drifted when the ice was thicker. And this was kind of cool. This study was done before the Mosaic expedition happened, but it kind of provided some guidance to like what kinds of tracks we might expect. And in fact, Mosaic did go pretty fast. It did drift pretty fast. So this was kind of some of the information that was useful for trying to understand that. So if you're interested in this paper where we looked at the different drift tracks and how they could be changed by a sea ice that's younger and thinner, you can look at this article. It's written by Alice de Vivier, who's pictured here, along with the co-authors at the bottom. This is me here. And yeah, it's just a fun paper to kind of bring some of the scientific literature to this discussion here. So that's all I have here. I'll make this presentation available to John. It has a bunch of teacher notes and website links and other things in it. So I think it'll be helpful for you, hopefully. And I'm happy to answer any questions that you might have.
Awesome. Great. Thanks so much, Jen. And I also want to say that I am recording this as well. So we'll make sure to update Google Classroom to include these slides, which, as Jen just mentioned, yeah, they have different speaker notes and links to things that you can check out in more detail, as well as this recording. So we'll make sure those are both on Google Classroom. So with that, yeah, we'd like to open it up for Q&A. And I know that this group has some questions, so either in the chat or feel free to unmute yourself. Who would like to ask the first question? Ruse.
Hi.
Oh,
I'm sorry.
Ruse, why don't you go, and then Tori, we'll have you go next.
Thank you.
Awesome. Ruse, we can't hear you right now, Ruse.
Sure.
You want to try again, Ruse? Yep, we got you now.
Oh, good. Oh, sorry about that.
No worries.
First, I just wanted to say a huge thank you, Dr. K, for everything you've done to help make this workshop happen. My question was regarding this. I think it was the second image that you had. It was a visible light image of the North Pole, and there was a black spot in the middle of the ice. You pointed to it and then didn't say why. Is that a spot with no ice, or what was that black? It looked like the eye of a hurricane or something, but I know it wasn't that.
Yeah, so that is actually where polar night is starting. So polar night is going to start at the North Pole. And if you look at these visible images, for example, in October, you'll see that eye grow. And it's basically because you can't see there. And so I think that could be a super fun thing to show your students, just like, we can only see so much, right? Like, and if we use different wavelengths, like not the ones that our eyes see in, but for example, longer wavelengths where there's radiation being emitted, or even longer wavelengths where there's still radiation being emitted, but it's, maybe at something related to the sea ice cover. This is the passive microwave. We can learn different things about the system. So I use that a lot when I teach undergraduates here at the University of Colorado, because I think it's really like visual.
Good. Great question. Thanks, Ruse. Thanks, Jen. Tori, would you like to ask your question?
Sure. Well, that was my first question. So thanks for asking that, Ruth. Do we have any graphics that compare the thickness of the Arctic sea ice to the Antarctic?
So thickness is one of these things that's a lot harder to measure. So we have measurements from ships where they go, but we don't have these, nice global maps of things from ships. We just have like a couple of tracks and stuff. And then we have satellites. They measure they're a different kind of satellite. They actually send a beam out and look for the response. And from that, they can tell the elevation of the sea ice. And from that, you have to make an estimate of how thick the snow is on top of the sea ice. And then from that, you can estimate how thick the sea ice is. But there's a lot of things that are going into those measurements. That's from an altimeter, a satellite altimeter. There's a lot of things that go into those estimates, and we only have them, you know, in recent years, like I would say in the last 10 years. So we know, for example, that the Arctic sea ice tends to be thicker than the Antarctic sea ice. The Antarctic sea ice tends to form and refreeze every year. But like exact quantitative, like change through time, those kinds of things are much harder to get for thickness than they are for the cover.
Chris, we've got those, you know, those great videos that show the Arctic amplification and that it's shrinking. Is there anything similar that they have in the Antarctic?
Yeah, well, this is one of the cool things too. The Antarctic doesn't have as much amplification as the Arctic. And, you know, this may be a question that you get, and it's one I get all of the time from my students, like, why is the Antarctic so different than the Arctic? And I think, first of all, it's important to acknowledge that that's a really important and good question, right? Like that's a question scientists are asking too, and, you know, that we are trying to understand. But also to emphasize that just because these are two polar regions doesn't mean that they operate in the same way. Like at the North Pole, we have an Arctic Ocean that's surrounded by land. And at the South Pole, we have a huge Antarctic ice sheet that's like, you know, very high elevation, lots of ice surrounded by the Southern Ocean. So the geography is totally different, like where the sea ice is living, where there's land. The sea ice in the Southern Hemisphere, it actually interacts with the mid-latitude storm track. So it sees a lot more storms and things like that. Whereas in the Arctic, you know, we're way up, you know, much higher latitudes where the sea ice is. So there's not as many storms. Another thing that's really important is that the ocean is a lot more stably stratified in the Arctic. So the surface of the Arctic Ocean, you can think of the Arctic Ocean almost like a bathtub, like it's surrounded by land on all areas, and all this water runs off into the Arctic Ocean. And all of that water is fresh water. And so it sits on top of the Arctic Ocean, and it actually prevents a lot of mixing in the surface Arctic Ocean because you have this freshwater cap on top of it. Whereas in the Antarctic, that's one of the areas where the ocean is the most deeply mixed. And you don't have this kind of ability to just kind of trap a bunch of fresh water because, you know, Antarctica can melt and there can be freshwater inputs, but it's going into this huge Southern Ocean all the way around Antarctica. So I think asking those questions and thinking about the difference between the Arctic and the Antarctic is really fun.
Thank you.
Sure.
Thanks, Tori. Jen, I'm going to go to the chat real quick and kind of connect two questions. You know, why did you go into this study, this field, and what advice would you pass along to students who might also be interested in a career in climate science?
Yeah, I mean, I first got interested in the Arctic in 2007 when we saw that really dramatic decline in Arctic sea ice. And I was working as a scientist at that time, but my specialty had been more about clouds. So I just got fascinated with the Arctic because it's just changing so much. And so it was just really fascinating to me. And I also always like things that were cold, so that helps. This question about students who are interested in a career in data science, wow, that's a great one. I would say get more experience with data science, with climate science. You know, look, don't be scared of programming and data analysis, and any opportunity that you have, you know, both in school and outside of school, to do, you know, research internships or take classes that have projects. That's the kind of thing that's going to help you see if you really like being a scientist, if you really like these kind of inquisitive and answering these, you know, why questions about why these things are happening. I'll just do a quick plug that my department at the University of Colorado this summer, we're doing a virtual REU, a research experience for undergraduates. And it's been so inspiring, like, because it's virtual, we've been able to engage with students from all over the country. Like, I'm working with a student who's actually in Texas. He's an undergraduate in the University of Texas, Rio Grande Valley. And just talking to him about the Arctic has been really, really fun. And he, I think, is really enjoying the ability to interact with all of these data sets. So, you know, I think research experiences, research internships, you know, don't be scared to jump in and ask some hard questions and try to get some answers.
Yeah, thanks, Emily and Renee, for that question. Wehunt, do you want to unmute yourself and ask your question, please?
I had a bunch of different questions about the thickness of the ice, but I'm just going to go with this one. Does the thickness of the ice, I know the shrinkage does, but does the thickness of the ice impact the reflectivity of the ice or the albedo?
Yeah, I mean, when the ice gets really thin, it can start to darken. So, for example, I know this from firsthand experience because I was on the Arctic sea ice north of Alaska, and it was only about 40 centimeters thick. And it looked a lot darker than, for example, the sea ice that Jonathan has in his background image there. But there's also, it's important to emphasize that that sea ice thickness can affect the albedo, or how bright the sea ice is, indirectly as well. And how is that? Well, for example, because snow is really important for how bright the sea ice is. And so if you have thicker ice that is maybe just around longer when it's snowing in the Arctic, you might accumulate more snow on it. And that bright snow might keep the sea ice brighter for longer during the melt season. If that makes sense. So there's a lot of different ways that thickness can affect the Arctic sea ice cover. And, you know, I wish we had better long-term measurements of it. I mean, what we have is great, but having more would be awesome. So if your students have any great ways of thinking about how to measure Arctic sea ice thickness from space, like, we're all ears.
Great, thanks, Wehunt. Rama, we'll go to you, and then Ruse next after Rama.
Dr. K, thank you so much for your expertise. My question is, when the Arctic ice melts and the thickness of it decreases, did you guys find any differences in the type of sampling? There is a change in the type of either chemical or microorganisms or whatever that you're looking for. Was there a change in the whole situation, or was it the same sampling between the layers that you collected? Because before you were collecting from probably 40 meters, now it's melted. Now you probably can collect from 60 meters. You know, was there a difference in that sampling itself?
Yeah, that's a good question. And maybe I'll just clarify how thick the sea ice actually is, just so you guys have a sense of it. So sea ice, it grows, let's say you just have some open water and you want to grow some sea ice, right? So first ingredient, you got to get it cold, like -2, right? Celsius cold. And that first sea ice that grows, it's going to grow really fast because it's growing as a consequence of the temperature gradient from the cold air above it to the air, to the cool, the ocean above it. So when it goes really fast at first, but by the time you get to about 1 meter, so about 3 feet, if the sea ice is growing from the bottom, it's much harder for that sea ice to grow because basically it's pretty insulated from that really cold air above that's causing it to thicken. So once you get to about 3 feet, in order to thicken the sea ice more, you have to have some basically dynamical processes, some crunching of the sea ice, some deformation of the sea ice. And so what you get are these things are called ridges. And it's basically where, like, the wind is piling up the sea ice and you can get thicker sea ice. And we see the thickest sea ice actually in the Arctic off the north coast of Canada and the Canadian archipelago. And that's because that's where the winds tend to pile up the sea ice. But the thickest sea ice we see there is like maybe 6 feet, 7 feet. It's not 30 meters. No, it's pretty thin. And when we're talking about, you know, sea ice changing from, you know, kind of this older, thicker sea ice pack to this kind of newer, you know, younger, thinner ice, we're talking about going from like 6 feet to, maybe more like 2 or 3 feet. And that's because every winter it's going to get cold in the Arctic. And so you're always going to be able to form that first layer of ice. It's just you may have as many opportunities for it to get like crumpled up and to grow thicker if you only have a year before it starts to melt again in the next summer. I don't know if that answers your question, but yeah, in terms of thinking about like microbes and things in the sea ice, there's definitely things that are alive in the sea ice, and I have colleagues who study them. But that's not my particular area of expertise. But if you're interested in kind of what they're seeing as the sea ice thins and how the organisms are changing, there's certainly changes in the Arctic Ocean because the sea ice cover also can block solar radiation, shortwave radiation from going to the surface ocean. And so things like, that rely on that to photosynthesize in the surface ocean, they're probably pretty happy in the Arctic right now, right? There's a lot more sunlight coming to them. And so there's definitely changes in some of the ecosystems up there, from the smallest critters that are photosynthesizing all the way up through the polar bears.
Thank you. Thank you.
Great. Thanks for your question, Ramu. I think that you kind of answered, Jen, the question in the chat about decreasing sea ice and people and animals and how some are going to thrive and some might be affected in other ways. And so I think we'll leave that question and we'll end with Ruse here just so we can get back to the workshop and lunch. Ruse, we'll have this question be the final question. And then just like Jen mentioned, any questions that you have, you can put to us and we can send them to Jen, or you can reach out to Jen directly after this. But just for the sake of time, Ruse will have this be the last question and then we'll get going. Go ahead, Ruse.
Okay, Jen, thank you for distinguishing between conceptual models and numerical models, which have predictive power. You showed a graph that showed the trend line of the Arctic ice thinning. If that trend continues, do you know, what does the model say in terms of when will there be no sea ice in the Arctic in September? What year?
This is a great question. I love it. Because I have a very, very specific answer that may surprise you in its lack of specificity. So I will say sometime in the middle of this century. And you're going to say, why isn't she saying 2049 or 2042? Why isn't she giving me a specific answer? Does she just not know? And the answer to that is yes, I do not know. And yes, there's no way we will ever know. Like if somebody tells you something's going to happen in 2049, you should ask them, why do you have that level of precision? There's a lot, as we saw in the time series, a lot of variability in what happens year to year. And a lot of that variability is not controlled by things like increases in greenhouse gases. There's, whenever there's climate change, there's always climate variability still there. And so this answer sometime in the middle of the century is kind of informed by my understanding of what that variability is, and also kind of what the change is that we're seeing in our models as we change things like the greenhouse gases into the future. But yeah, that's a great question.
Thank you.
Yeah. If it's okay with you too, John, I'll just really quickly answer the 2 questions that you had posed to me this morning on email. The first was about like what makes a gas in the atmosphere a good greenhouse gas, and that is its ability to absorb and emit radiation, because that's what good greenhouse gases do. So what makes that a particular gas good at that is it has to basically have like rotation or bending modes. So for example, water, H2O, it can absorb and emit radiation because of its structure. In contrast to something like nitrogen, and we have a ton of nitrogen in the atmosphere, but nitrogen doesn't bend. It doesn't have the ability to absorb and emit radiation. So I often tell my students it's kind of like, some people at a party like to dance and, get out there and move. And some people are just like stand by the side of the wall. Like the greenhouse gases are the ones that like to dance, right? They can move, they can absorb and emit radiation, they can do a tango. And the kind of inert gases that are not greenhouse gases, they're kind of like the wallflowers. They're like standing on the side, they're not big dancers. That's cool. Like they're just drinking some punch. It's all good. So yeah. The other question I think was like why we use a particular time period as kind of a long-term mean. And in particular, I think the time period that was mentioned was maybe a little bit older, like 1951 to 1980. This is an important question. There's two aspects of it. I'll just say first, like we always use a long-term mean, usually about 30 years, because we want something that's pretty stable climate-wise, and 30 years is kind of a good rule of thumb for something that's long enough to compare to as kind of an average. But the exact time period we use, that's a really good question, because of course the climate is changing. And so if you use a time period, for example, let's say you calculate the anomaly of the Seattle heat wave that just happened this week. If you calculate the anomaly relative to the current 30 years, it's not going to look as extreme as if you calculated it compared to, for example, earlier in the 20th century, where it wasn't as warm. And you could probably pick different 30-year periods to make that heat wave look more or less extreme. So you have to be careful with your choice of a reference. And it's one of these things that's a little bit subjective, but the main thing is to pick a period that's long enough, and also to pick a period that's kind of representative of the climate that you're trying to compare to. So yeah, hopefully that helps.
Yeah, thanks so much, Jen. We really appreciate you being here and taking the time to answer these questions. And again, sounds like some folks might reach out with additional questions, but we'll make sure to post your slide deck and a recording of this talk to Google Classroom later today or tomorrow. Thanks.
Sounds great. Thanks so much for the opportunity, and lucky you guys to have John, Lynn. What a fun crew to be spending your day with. Enjoy them.
Lucky us. Thanks, Jen. We really appreciate it.
Yeah, take care all.
And
Thanks, Jen.
before we depart for lunch, we're gonna have Lynn take over for a few minutes here, and during lunch, we're gonna ask you to complete a quick task. And so we'll have Lynn introduce this task and then send you away for lunch.
Great, thanks so much, John. Yeah, so like John said, I'm just going to introduce the next lesson in our unit here, and then give you all a short task to complete during your lunch break. And just to kind of bring us back to where we are within this unit. So John mentioned yesterday that we started out with this question about our phenomenon of the Arctic warming twice as fast as the rest of the globe. And then we zoomed out and looked at the globe from a bigger picture view. So we were kind of looking at the Earth's energy budget as a whole and trying to understand that better and what's going on in the atmosphere. And now we're going to go and zoom back into the Arctic and start thinking about the processes that are specific to the Arctic. And a couple of you had questions that came up for Jen that related to albedo. So it's great that you're already thinking about that. And that's kind of the direction we're going to go in here. So for lesson 6, measuring albedo, students use